In this video, I'm going to use these properties here to evaluate the Laplace transform of some functions. So being able to use these properties is going to come in handy, because in some cases it might be the only way we can find the Laplace transform of certain functions, or even if it's not, it might work out more efficient than plugging in the definition of the Laplace transform. So in the first example, we're going to find the Laplace transform of sine squared t. So this one we are going to work out using this property here, the Laplace transform of a derivative. So what we are going to do is we are going to first differentiate this. So derivative of sine squared is going to be 2 sine t cos t. That is the same as sine 2t. Then what we're going to do is we're going to take Laplace transforms on both sides. So Laplace transform of f prime is going to be the Laplace transform of sine 2t. And then for sine 2t, we're going to use the tables of Laplace transforms. And from there, we are going to find that the Laplace transform of sine 2t is the s over s squared plus 4. By the way, in those tables we won't find s squared. And then on the left hand side, using this first property here, we can write this as s times the Laplace transform of f minus f at 0. Now remember, f is sine squared, so f at 0 is going to be sine squared at 0, which is 0. So that means this term here is going to be 0. So from here we can make f the subject of the formula. So the Laplace transform of sine squared is going to be equal to 1 over s squared plus 4. Just one moment there. Alright, so apologies here, there is just a typo. The Laplace transform of sine 2t is 2 over s squared plus 2. So this is going to look like that. So that's going to be the Laplace transform of s squared. In the second question, we're looking for the Laplace transform of t squared e to the minus 2t. So here we're going to use the fact that we can find the Laplace transform of e to the minus 2t from the Laplace transform tables. So that one we can just read out. It's going to be 1 over s plus 2. So the Laplace transform of t squared times that, we can use this property here. So our f of t, if you like, is going to be e to the minus 2t. So maybe we should use different notation, but according to that, the Laplace transform of t squared e to the minus 2t, according to that formula, it's going to be the second order derivative of the Laplace transform of this one which is 1 over s plus 2. So all we need to do is just to differentiate that thing twice. Differentiate it once, we get negative 1 over s plus 2 squared. Then differentiate it again, going to be 2 over s plus 2 cubed. Okay, this point we're going to give you an opportunity just to have a go at this one. Laplace transform of t times cosine at, where a is a constant. So what you can do is just pause the video and work through this thing, and then when you continue the video you can compare with our solutions. Okay, we're now going to scroll down to our solution for C. We hope this work is useful. We do of course implore you to subscribe to our channel, and if you've got any questions or comments, you can post them in the comments section. So for this one, again, we've got t times some function. So that means we're going to use this last property here. Since the power is 1, so it means there's going to be 1 and 1 there. So the way it's going to look like is as follows. So the Laplace transform t times cosine at is going to be the negative of the first derivative of the Laplace transform of cosine at from the Laplace transform tables. This one is s over s squared plus a squared. So then just differentiating this once by the quotient rule, it's going to give us this here, which simplifies to that. So that's going to be the Laplace transform of t times cosine at. All right, thank you for watching. In the next set of videos, we're going to look at Laplace transforms of functions involving the Heaviside function. All right.